My name is Charles Draper. I'm the chairman of the Herschel Society. Welcome to the 2025 Caroline Herschel Prize Lecture to be given by Dr. Vicky Fawcett of Newcastle University. As always, first things health and safety. Not expecting a drill tonight. If the alarm goes, leave by the back doors, go across the hall and into the courtyard where we'll get very cold. The Caroline Herschel Prize Lecture was established in 2018 by our society in association with the RAS to celebrate Caroline's memory by supporting promising women astronomers early in their careers. It's now in its 8th year. We're very grateful to a variety of people. Professor Fran Bagenal of the University of Colorado in Boulder, who made a major donation to help fund it. I think she's on the line tonight. The RAS are associates in practical help in making it work. And I'm very glad that Dr. Imogen Gingell, a council member of the RAS, will be saying a few words shortly. Professor Mike Edmonds, who's an ex-RAS president, but also our vice president, who was very helpful in setting out the process and establishing the RAS connection. And Professor Lindsay Fletcher of the University of Glasgow, who is online and will be speaking shortly, and her colleagues on the panel, who have the task of selecting the winner. Lindsay will also speak shortly. And finally, the University of Bath of hosting, including their staff here tonight, who are being very helpful as always. So why celebrate Caroline Herschel? Caroline was born, like her elder brother William, in Hanover in the mid-18th century. Unlike him, she was given little education and was destined to a life at home of domestic drudgery. William became a successful musician in Bath in the 1770s and brought Caroline here for his and her sakes. She, in turn, was an effective housekeeper, a talented singer, and later, after they left Bath, a very useful observing assistant. Fame from discovery of Uranus took them both to Slough in the 1780s and close contact with the King's court. Important visitors and astronomy filled their days and nights. Goodness knows when they slept. Caroline was increasingly recognised as an astronomer in her own right. She got a pension from the King as the first paid female astronomer. She made many discoveries, including 8 comets and several deep sky objects. Most importantly, William and Caroline's system of communicating and recording the observations pointed the way for astronomers today in terms of how you separate the collection and analysis of data. Caroline returned to Hanover after William's death and carried on cataloguing the night sky, mainly to support her nephew John Herschel's observations. This led to the precursor of the new German catalogue of deep sky objects still in use now. Caroline was awarded the RAS Gold Medal in 1828 and many other honours subsequently. She made a real mark in an age where women in science were almost unknown. No wonder she is an inspiration for so many today. I'll now hand over to Dr. Imogen Gingell to say a few words on behalf of the RAS. Imogen.
Thank you. I hope this mic is working now. It is, great. So my name's Dr. Imogen Gingell. I am a counsellor for the Royal Astronomical Society and an astronomer myself. It is a privilege to be here, to be invited to speak on behalf of the RAS. I know how important these kinds of schemes can be, both personally, also being a kind of early to mid-career woman in astronomy myself. So I definitely want to say, I can speak for all of the RAS and all of the council, indeed all of our members and fellows, I think, when I say we put our strong support behind initiatives like, our partnership with the Herschel Society and the Caroline Herschel Prize Lectureship more specifically. It's so important to support the careers of women in our field and early career scientists both. I see this all the time personally in my role where I work a lot in quality, diversity and inclusion in the University of Southampton. And I see how important these kinds of prizes and recognitions and things, how much momentum they can put behind careers and kind of make sure we can address some of the imbalances that were sadly present while Caroline Herschel was doing the great work that she was doing as a pioneer in our field. So my personal congratulations to Dr. Vicky Fawcett for this prestigious lectureship, and also the congratulations of all the RAS Council. And I'm looking forward to listening to your talk.
Thank you. And now Professor Lindsay Fletcher, who is the chair of the panel of judges, will talk about this year's competition.
Okay, good evening, everybody. Can you hear me?
Yes.
Okay, great. Thank you. So good evening. It's really a great pleasure to join you online this evening. I'm sorry I'm not there in person, but it's a long way from Glasgow to Bath. So I would just like to applaud and also echo the comments made by Charles and by Imogen about the importance of the Caroline Herschel Prize Lecture for the recipients of the lectureship, but also to the Herschel Society and to the Royal Astronomical Society in their sterling work in recognising and promoting women astronomers. So, as mentioned, I had the great privilege of chairing this year's Caroline Herschel Prize Committee together with the other members, Professor Jane Birkby of the University of Oxford and Professor Paula Chadwick of Durham University. And I would really like to thank them here tonight. We had a great time reading the applications from a large field of very impressive candidates who are working in diverse areas of astronomy, from asteroids to gravitational waves. The prize lecture rightly recognises the different ways that people contribute to astronomy. And so we looked at the candidates' research, their outreach, and also their teaching activities. And there were very many genuine standout achievements by the people who'd applied for this lectureship. And to us, this really emphasised the ongoing strength, impact, and importance of the contribution to astronomy by these women at an early stage of what we hope will go on to be long and rewarding careers. However, after all of the fun of reading and discussing, we had the difficult task of selecting this year's winner. And after some deliberation, we were unanimous in recommending Dr. Vicky Fawcett. Dr. Fawcett has demonstrated excellence in her research, which is reflected in her many publications on quasars and their environments, and also her co-leadership of a working group in this area within a major international project called the Dark Energy Spectroscopic Instrument, or DESI. Moreover, she has an outstanding track record in outreach and communication, focused on astronomy local to the northeast of England and aiming to engage its young people, their families, and the wider community in science, technology, engineering, and mathematics subjects. She's known for her clarity and her enthusiasm when delivering public talks, and we felt that her lecture topic would be of great interest. I'm very much looking forward to learning from her. Congratulations, Vicky. Thank you.
Almost there. Vicky will talk for about an hour, and then we'll have questions afterwards. If you're in the room, obviously keep your questions until then. If you are online, please put your questions in Slido, and you have access to that, or you can use the QR code there, and I'll pick them up here on the screen at the end. So without further ado, I now invite Dr. Vicky Fawcett to give 2025 Caroline Herschel Prize Lecture on Unveiling the Secrets of Hidden Supermassive Black Holes. Vicky.
Okay, can everyone hear me? Yep, okay. So, yeah, hi everyone, and well, thanks for that really lovely introduction. So, yeah, my name is Dr. Vicky Fawcett. I'm an astronomer at Newcastle University, and I just want to start by saying that I'm really genuinely honoured to receive this award, especially being named after Caroline Herschel, the first woman to receive a gold medal from the Royal Astronomical Society. And it's interesting that I come from Newcastle University because my department's actually in a building called the Herschel Building. And this is named after Alexander Herschel, who's actually the grandson of William Herschel, the famous Herschel that discovered the planet Uranus here in Bath. And Alexander Herschel was the first professor of physics at the University of Durham College of Science, which is now known as Newcastle University. So it's quite a nice link to where I work. So today I'm going to be talking about supermassive black holes and also my research which focuses on hidden dusty black holes. But we're just going to start from Earth. So here's a really lovely photo. This is in Chile, and these 4 telescopes make up the Very Large Telescope, or the VLT. So a recurring theme of this talk is that astronomers are not great at naming things. We're pretty direct. And if you're lucky enough to be in a dark sky location like the desert in Chile, this is kind of what you'll see. So an amazing sky kind of full of stars, and running across it, you can see the band of the Milky Way. And for quite a long time, people thought the stars in the sky were kind of fixed, they were eternal, they would live on forever. But we now know that kind of much like ourselves, stars are born, stars grow, and eventually stars come to an end. And it's that end that can give us some of these very exotic black hole objects. So let's just talk through a little bit of stellar evolution. So how do you birth a star? So we start with what we call a star-forming nebula, which are these giant clouds of cold molecular gas in the universe. And probably the most famous one of these star-forming nebulas, and probably everyone here is sort of familiar with this picture, are the pillars of creation. So here on the left, I have an optical image by the Hubble Space Telescope, and on the right, the relatively new James Webb Space Telescope, which sees an infrared, which is why you see some differences. And what you see is these giant pillars of these cold molecular gas clouds, and these are actually stellar factories. So what happens is this cold gas clumps together, and then under gravity, it keeps clumping together, and until eventually, when you have a big clump of gas, the center under friction, starts to heat up. And when it starts to heat up, what you develop is a baby kind of protostar. So this is what I call a little baby star. And then after millions of years, these protostars get kind of so big, and there's so much pressure and temperature in the core of these protostars that hydrogen can fuse together under nuclear fusion. And from this, you birth kind of typical stars. And stars actually come in a variety of sizes. So we have, I would say, typical or low mass stars, a bit like our sun, but you can also get much, much bigger stars. And also an interesting thing is that bluer stars are hotter and redder stars are cooler. So this is kind of maybe the opposite to what we think. We associate red with heat, but if you think of a Bunsen burner or a fire, the blue part of the flame is the hottest part. So I have a little video just kind of giving a sense of scale of the universe, but in terms of stars. So we're going to start from the Earth and then look at different types of stars relative to the size of the Earth. So moving up in size, we go to the largest planet in our solar system, Jupiter, which is about 11 Earths across. And then if you get a little bit bigger than Jupiter, you get the smallest stars you can form. So just a little bit larger. And these are your red dwarfs. And then moving up in size, like I said, the sun is kind of small to medium mass, but you can get much, much larger stars. So Sirius A, the brightest star in the sky, and then on to what we call the red giant stars. And if you notice here, this is the sun down here. So you see that we're really kind of scaling up in size. So now on to our kind of blue giants, but we can go even bigger than this. We can go up to the next level, which we call our red supergiants. And there's quite a famous red supergiant that you've probably heard of, which is this one, Betelgeuse, which is what you see in the constellation of Orion. All the way up to this guy, Canis Majoris, which is one of the largest stars we've ever discovered. So this kind of just gives you a sense. We think of the sun as being this enormous object, and it is, but in space you can get much, much bigger. And I'll keep referring back to the kind of sheer scale of the universe in this talk. Okay, so now if we follow our low mass track, so luckily, once you're in this kind of stable star phase, you last for quite a long time. So the sun, for example, it has 5 billion years left, so don't worry too much. I'm sure we have other problems to solve within 5 billion years, but eventually it will run out of fuel in the core to kind of stop burning. And when it runs out of fuel, it puffs up into this red giant phase, and this is what I call the old age of the star. And then eventually, this red giant will kind of blow off the outer layers of the star into space and create probably one of the most spectacular images we have, which is a planetary nebula. Confusing name, nothing to do with planets, but again, a lot of names stick in astronomy. So I just picked out two, again, with the James Webb Space Telescope, our new favorite kind of toy as astronomers. So these are two ring nebulas, and what you see, this kind of circle of matter, this is actually the layers of the star kind of being blown off. And what you're left in the center is a very dense, what I refer to as kind of a fossil star, which, if you're on the low mass end, is a white dwarf. And this then just cools slowly over time in kind of billions of years. But just a note of caution when talking about the fact the sun's going to die, and this is definitely not from personal experience. Don't tell very young children that the sun is going to eventually explode and we're all going to die, because it turns out very young children don't understand the concept of time. So just, if you're ever talking to a primary school, again, definitely not personal experience, just caution that this is a very long time in the future. Also, this is the only meme in this talk because I'm too old for this now. Okay, so if we go in the high mass track, it is pretty similar. Instead of a red giant, we get a red supergiant. But the difference in these high mass stars is nuclear fusion can keep going. So hydrogen goes to helium, helium goes to carbon, you kind of keep going up until eventually you reach iron in the core. And the interesting thing about iron is if you want to fuse two iron together, you actually have to put energy into the system. So basically, you get to the point where the star's no longer releasing energy, and that means there's nothing to counteract the gravity of this star. So gravity wins, it starts collapsing, and then explodes in a very violent, what we call supernova explosion, which kind of throws off a lot of these elements into space. And what's left in the center just keeps collapsing down. If it's a low high mass star, so kind of roughly 10 to 20 times the mass of our sun, will end up as a neutron star. And neutron stars are these incredibly dense stars kind of packed with neutrons. But if we're on the higher mass end, so we're now talking like 20 times the mass of our sun, you keep collapsing down into a singularity. And this is how you kind of birth these very exotic black hole objects. And these are the things that I like to study. So black holes, they're incredibly dense objects, and they're so dense and they have so much gravity that nothing, not even light, can escape. So what I mean by that is if we're unfortunate enough to be in our little rocket and we're heading towards this black hole, and yes, you can expect high-quality animations like this throughout, and we fall into the black hole, even if we've developed some sort of speed of light capability, so our rocket can maybe travel at the speed of light, you would never be able to escape the black hole. And another kind of interesting thing about black holes is, say you were falling in feet first, again, hopefully this won't happen to you, the gravitational pull on your feet compared to your head will be so different that you'll actually get stretched apart like spaghetti. And the scientific term for this is spaghettification, which you can look up, I'm not making this up. This is the process of objects getting elongated as they fall into black holes because of the kind of incredible strength of the gravitational field. So there's two sort of important properties of a black hole. So this is an artist impression. Most of the things I'll be showing are artist impressions. What you always see this kind of bright disk of matter around the black hole. And we call this the accretion disk. And this is a disk of kind of material that's orbiting the black hole. So the planets orbit the sun because the sun has a lot of gravity. The same thing happens around a black hole. The black hole has lots of gravity, so all this material and kind of dust and stuff is orbiting the black hole. But the black hole has so much gravity, they're kind of whizzing around at great speeds. And they rub together, and this friction causes heat, and this heat causes a lot of light. So you always see this really bright disk of matter that's slowly falling into the black hole and feeding it. You also probably notice a lot of these images, you see this sort of kind of halo of light around the black hole. And that's because the gravity of the black hole actually bends light. So what you're seeing is the accretion disk from behind the black hole being bent over. And that's what causes this circle. And for those of you that are into films, this is actually taken from the film Interstellar, which is a great film. And the filmmakers actually wanted to make Interstellar quite scientifically accurate. So they went to Nobel Prize winner Kip Thorne, I'm assuming gave him some money, time on a supercomputer, and said, can you simulate a planet going around a black hole? And this is the direct image from the simulation. I think they made it a bit more pretty for the film, but they did it, and they worked out you could have a planet orbiting a black hole at a safe distance. So there's quite a few things in Interstellar that are actually scientifically accurate. So for example, when they visit this water world and something happens and an hour passes on this planet and back home 50 years had passed, this is a real effect called time dilation, and that's because time is slower around strong gravitational fields. So time actually is slower if you're on a planet by a black hole relative to the Earth. The thing that maybe isn't scientifically accurate is the end of Interstellar, and there's something to do with falling into a black hole at a bookcase, but, we give them a little bit of artistic license at the end. The last thing is the event horizon. So this is the point of no return. So once you're past the event horizon, you can never escape a black hole, even if you're traveling at the speed of light. And so when we kind of talk about the size of a black hole, we normally are referring to this kind of distance, this event horizon. So because black holes are such kind of weird and strange objects, this is my favorite way to think about them. So if you think about space, or space-time as we say, as a blanket, and if you drop different masses in, it will create a dip in this blanket. So a light mass, like a planet, you could think of as a kind of a golf ball, would create a little dip. If you had a big mass, like a star, that would be like putting a bowling ball on this blanket, and this creates a large dip. And you can think of the depth of this dip as the strength of gravity. And so if I'm a little planet here, and I'm kind of traveling through space, I'm going to fall into this dip, this kind of gravity well, and I'm going to start to orbit this star. So this is also how you can think of the orbits of the planets. So now what you can think about is a black hole is like taking this blanket and pulling it down to infinity. So now if we're unfortunate enough to come close to the black hole, we're going to fall into the black hole and then just keep falling forever. And this is sort of where the name black hole comes from. They're black because they don't emit anything, light can't escape, and they're holes because you can sort of think about them as a hole in space. So maybe that helps, maybe that confused people more, but that's how I kind of like to visualize a black hole, is this curvature of space-time, but in an extreme fashion. Okay, there's only a tiny bit of audience participation in this talk, don't worry, and you can just think about it in your head. But I always get asked the question, again, especially from school children, that I'm definitely not trying to scare with this topic, but how far is the closest black hole to Earth? Like, do we need to worry about these objects? And to answer this, we're going to use the unit of light years. So light is the fastest thing in the universe, but it's not instantaneous. It has a fixed speed, which is roughly 300,000 kilometers per second. So when people are talking about light years, 1 light year means the distance it takes light to travel in 1 year. And this is equivalent of about 6 trillion miles or 9.5 trillion kilometers. And for reference, the light from the sun takes 8 light minutes to get to Earth. So thinking about that, how far do we reckon the closest black hole to Earth is? And you can think about this in your head. And I'm going to, maybe slightly unconventionally, think about this in the travel distance between where I came from this morning, which was a little bit dicey with the snow in Newcastle, but I made it, it's all good, to Bath. So the journey from Newcastle to Bath is about 324 miles or 521 kilometers. So the closest black hole to Earth is the equivalent of me doing this journey about 27 trillion times. And if you work that out, it's about 14 quadrillion kilometers, or in our slightly nicer units, 1,500 light years. So this demonstrates 2 things. Well, one, you don't need to worry about black holes. The closest one we found is it still takes light 1,500 years to travel from that black hole to Earth, but also why astronomers tend to use strange units a lot of the time, because it would be quite difficult to constantly be talking in quadrillions of kilometers all the time. And this is relatively close by, which we'll talk about later in this talk. So the other question I get, how do we even know black holes exist? You know, they're black, we can't see them. So one of my favorite ways is looking at the motions of stars around these objects. So again, this is a nice VLT image. This is the center of our galaxy. And if we zoom right into our galactic center and observe the stars, this is kind of what we find. So each of these bright dots is a star right at the center of our galaxy, and these are real observations that we've taken over about 10 to 15 years. And pay attention especially to this one here. What you see is that it seems to orbit something in a very eccentric orbit, and it seems to kind of be slingshotted around something. But you can also see that you can't really see anything at the center. And what we can do by tracking all these different stars, and we can track quite a few of them, we can plot their orbits, and this is what it looks like. And you can see they're all sort of orbiting something here. Then we can use Kepler's laws of motion and work out how much mass is enclosed in these orbits. And when we do the calculation, and we have quite a few orbits to constrain this, we find that it's a few million times the mass of our sun that's at our galactic center. And the only known object, this is a relatively small space for a few million suns, is a black hole. The other way we find black holes is through binary systems. And the 2 main flavors are a black hole star binary or a black hole binary. So I don't have time to talk about the black hole binaries, but I'm happy to talk about this after my talk. So focusing on this black hole star binary, this is a little animation. Here's your black hole. You see this accretion disk that I'll keep talking about. And the gravity is so strong, it can actually strip material off its companion star. And when a black hole consumes so much material, what happens is it can sometimes flare up. It can sometimes launch highly relativistic jets that are observable in X-rays because they're so high energy. So what we do is we can observe these in the X-rays. We call these X-ray binaries because they're so bright. And we can infer there's a black hole with a stellar companion. So all of these methods that I've been talking about are indirect ways that we can find black holes. They're just ways that we can infer a black hole probably exists there. And a lot of people kind of doubted the existence of black holes. They thought it was a nice kind of theoretical, mathematical concept, but are these weird holes in space-time, do they actually exist out there? And so the best way we know that black holes definitely do exist is that we've taken a photo of, well, of two now. So this video, yet again, we're zooming into the center of our galaxy, kind of by the constellation of Sagittarius, and these are real images now. So we start off in the optical, and as we zoom in further and further into our galactic center, we switch to infrared and eventually switch to kind of radio wavelengths. And that's because imaging the center of our galaxy is actually really hard. There's just so much kind of dust and stars in the way. But if we keep going and image right directly in the center where we saw those stars orbiting something, this is what we see. So this is an image, a photo of the supermassive black hole at the center of the Milky Way, Sagittarius A star. And I'm sure some of you are familiar with this image. So this image was taken in 2022. It was actually the second supermassive black hole to be imaged. The first was in 2019, which was in the galaxy M87. And it's only a mere 27,000 light years away because it's within our own galaxy. Then again, that just kind of demonstrates how large our galaxy is. And we can do quite a lot of physics with just this image. So you can see here, in the black circle in the middle, this is the shadow of the black hole. And when we measure the mass of this black hole, we find that it's about 4 million times the mass of our sun. You'll also notice this bright ring, and this is this accretion disk and the light being bent around the black hole, like I was mentioning earlier. We can also do other funky things, like we can work out how fast this black hole is spinning. So quite a lot of impressive things we can do just from this image. So how do we even take images like this? Well, we took it from using a telescope called the Event Horizon Telescope, or the EHT. And I kind of mentioned that this image was taken in radio wavelengths. And quite a cool thing you can do with radio telescopes is you can link them all up together to make a bigger telescope. So what the EHT is a collection of radio observatories all over the world. So you have the South Pole, you have Hawaii, Chile, Spain, and others. They connect them all together and essentially make an Earth-sized telescope. And I think with the latest upgrades to the EHT, the resolution is so good that you'd be able to see a bottle cap on the moon from Earth. So it's quite an incredible telescope. You can actually apply for time, but convincing people to point all these telescopes at your one galaxy, you have to have a pretty good idea if you want to do this. So it took a team of international astronomers, kind of hundreds of astronomers. They took this image over several nights, stitched it together, and then that's what you get. And in my opinion, it's probably one of the greatest astronomy achievements in the last 10 years. I mean, that and gravitational waves, I think, in my head are neck and neck. So it was a bit of a shame when the first image came out and it was all over Facebook and people said, what's the big deal? It's just a fuzzy glowing donut. I actually think it's pretty incredible that we kind of, in this day and age, we can image a black hole. So I mentioned the term supermassive black hole. Again, astronomers not good at naming things. A supermassive black hole is just a really big black hole. So we refer to black holes as stellar mass black holes if they're like 5 to 10 times the mass of our sun. Supermassive black holes are hundreds of thousands to billions times the mass of our sun. And quite an intriguing thing that astronomers found is that in the center of almost all galaxies, there lies a supermassive black hole at the center. So including our own, the Milky Way, we have Sagittarius A star. So we think most galaxies have these kind of monster black holes right in the center. And how do you grow a billion mass, solar mass black hole? Well, we think that it's through accretion, which just means the black hole eating things. So the more stars the black hole eats, the more black holes merge with this black hole, it will get bigger. But there's a problem, and we'll come back to this, is that we're finding a lot of very massive black holes early in the universe. And our models don't actually work in terms of growing them big enough. But we'll come back to this problem later. So why do we even care? Why are supermassive black holes important to study? So there's this quite striking relation. I mentioned that galaxies have these supermassive black holes at the center. There's a tight relation between the mass of this supermassive black hole and the mass of the galaxy it's in. Specifically, the mass of the stars in kind of what we call the bulge, this kind of group of stars right near the center of the galaxy. And you find this tight correlation, which tells us that the galaxy and the black hole co-evolve over time. But we're not really sure how they co-evolve. And it's also, it's kind of intriguing they co-evolve at all, because although the black holes are 1 billion times the mass of the sun, spatially, they're so much smaller than the size of the entire galaxy. So how do these central supermassive black holes affect the way an entire galaxy kind of grows? And also, does the black hole form first and the galaxy forms around it? Or does the galaxy get big and then feeds a black hole that then kind of catches up? Or does the black hole and the galaxy sort of grow simultaneously together? And we're not too sure. And this is one of the things the James Webb Space Telescope is trying to solve. Understanding supermassive black hole growth. So I've already mentioned there's some issues with our models, so we really need to understand how do you even grow these monster black holes. And then finally, the thing that I'm most interested in is understanding how supermassive black holes that are consuming lots of material, which we call their active black holes, how do they affect the surrounding galaxy? So this is quite a famous galaxy with a very active black hole. And what I mean by active is that it's consuming so much material that it can launch these very powerful outflows and jets. So this is a composite image. This is the galaxy here. And what you see kind of launched far beyond the galaxy are these huge X-ray jet and radio jets. And this is launched by this black hole right in the center. And these jets and outflows must be doing some damage to the surrounding galaxy. Maybe stopping stars being formed, maybe just disrupting the whole kind of structure of the host galaxy. But again, we're not exactly sure what effect these active black holes have. So this segues me nicely into active galactic nuclei, or AGN. And this is just a term we use for these active black holes. So an AGN is a supermassive black hole at the center of a galaxy surrounded by this accretion disk that's so bright that it outshines the entire galaxy. And we say a galaxy is an active galaxy if it contains an AGN. So I've just told you that the Milky Way contains a supermassive black hole, Sagittarius A star. So do we live in an active galaxy? Well, probably thankfully for us, we don't. And that's just because Sagittarius A star is not really doing much. There's just not enough material around the center of our galaxy to feed our supermassive black hole. I think it consumes an equivalent of 100,000th of a sun every year, which is just quite a low rate. And to get these, very powerful active black holes, you need to be feeding them a lot more material than that. So when AGN were first discovered, they were discovered as these galaxies with these active black holes and this really bright accretion disk, really bright center. But then we started finding different subtypes, different flavors with slightly different properties. And because we're astronomers, we would give them a name or an acronym to be like, this is this subtype. So there's quasars, which I'll talk about. There's also Seyferts. There's different radio definitions, blazars, and type 1, type 2. And these are all defined on kind of the light that this object's giving out. In particular, differences in its spectrum, which we'll get onto spectroscopy later. And this paper tries to compile every subtype of AGN discovered, and these are just the main subtypes. It then goes on to the other subtypes, and as you can see, we love acronyms, and it actually just makes it really confusing and a bit of a mess. And it was known as the AGN Zoo, because there were just so many different objects. And it was getting quite chaotic. But then in the 90s, some people came along and said, all of these subtypes, they're the same object. We're just looking at this object in slightly different ways, which is why the light that we get in our telescopes is slightly different. So there's a lot going on in this schematic, but in the center, this is the model of AGN, where you have a supermassive black hole in the center. You then have this really bright accretion disk that's feeding the black hole. Slightly further out, you have what we call the dusty torus, which is a donut of dust that surrounds the accretion disk. And then you can sometimes get these kind of very energetic jets. And what the unified model of AGN suggests is, depending on how you're looking at this object, the light you receive will look very different. So you've got to remember these AGN are out somewhere in the universe. We're stuck on Earth. With our telescopes, we have one line of sight. So depending on how this AGN object is orientated, we're going to see different things. So for example, we could be looking directly down the barrel of the jet, or we could be looking directly at this bright accretion disk, or we could be looking directly through this dusty donut. And you can imagine the light you get from your telescope will look very different in each of these orientations. This video tries to explain what I've just said a little better. So we're zooming in to an AGN. You can see the center is very bright. And when we go right into the center, this is this dusty donut that I was talking about. And what this video tries to demonstrate is, imagine you're the telescope, and this is your viewing angle to the object. So right now, we're viewing the AGN through this donut of dust. So it almost completely blocks out the light from this accretion disk. But as our line of sight moves above this and kind of moves more face on, we start to get all this really bright light from this accretion disk. But all you really need to take away from that is the definition of a quasar is that it has this unobscured view to the accretion disk. So we're looking directly at this bright disk of matter. And because of that, quasars are they're classified as the most powerful type of AGN, the most luminous type of AGN. And the most powerful quasars we've discovered have luminosities or brightnesses that are about 1,000 times greater than the Milky Way. So imagine taking 1,000 of our galaxy, kind of putting them together, and that's how bright some of these quasars are. And I think in 2024, the most luminous quasar ever discovered was found, and I think the authors say that quasar that they found in 2024 is 500 trillion times more luminous than the sun. So it's pretty bright. So a little bit of history, why the name quasar? So quasar is actually a shortened version of quasi-stellar radio source. And this is because when they were discovered in the 60s, they were discovered in a radio survey as these very bright radio sources that looked like stars on the sky. They were kind of point-like on the sky. And they didn't really know what they were. They thought, maybe these were some kind of exotic new type of radio star. And so they were called quasi-stellar, star-like radio sources. So we now know quasars aren't stars. They're actually these very bright active galaxies. They look like stars on the sky simply because the center, this accretion disk, is so bright, it just blots out the other stars in the galaxy. So some people like to use QSO, or quasi-stellar object, to try and get away from this radio connotation. but you'll find quasar and QSO are used interchangeably. And yes, quasars can be incredibly bright in the radio, but they don't have to be bright, and that they typically are bright across the electromagnetic spectrum. So I keep coming back to the why question. Why do we care about quasars? So probably the best example we have is cosmology. So because quasars are one of the brightest objects in the universe, they're also one of the most distant objects we can see. Since fainter objects, our telescopes just wouldn't be able to pick up the light, unless you stared at a patch of sky for a really long time. But again, asking a telescope panel that you want, hundreds of hours of telescope time, you really need a good scientific case for that. So quasars are a good way to probe kind of vast distances. And a kind of funky thing with astronomy is the more distant, further away you look in the universe, the further back in time you're seeing that object. And this is again because light isn't instantaneous, it's the fastest thing in the universe, but it takes time to get from these objects. In this example here, you have like a distant source that's 11 billion light years away, and that means that the light from this object takes, roughly 11 billion years to get to Earth. So we're seeing this quasar 11 billion years in the past. Again, kind of ignoring the fact that the universe is also expanding. So what cosmologists do is they use quasars as sort of lampposts looking back in time, and then they can probe the kind of really early universe in order to understand how did we go from the Big Bang to the universe we see today. So personally, I'm not a cosmologist, but I appreciate cosmology and the use of quasars. So this is an artist's impression of the second most distant quasar. The most distant quasar was discovered in 2023, but this guy here kind of poses one of the problems I was speaking about earlier. So this is the nicely named J0313-1806, the second most distant quasar ever discovered. It's at a redshift of 7.64 if you're into the weird astronomy units of redshift. And this quasar is 13 billion light years away. So again, because light years are a bit of a weird unit, I'm going to do the equivalent of Newcastle to Bath. So if we wanted to travel to this distant quasar, it would be the same as doing Newcastle to Bath 240 quintillion times, roughly 120 sextillion kilometers away. And I had to look up how to say these numbers. So if we have our quasar and it's 120 sextillion kilometers away, we took our fastest spacecraft, which I believe is the NASA Parker Solar Probe, this satellite that goes around the sun, and this goes at roughly 150 kilometers per second. And then we just sent this satellite out to this distant quasar. It would take about 25 trillion years to send our fastest spacecraft to this quasar. Again, not actually taking into account the fact that the universe is also expanding and getting bigger. So this highlights space is really big, and it also highlights the kind of nuance of astronomy compared to other areas of physics. So in science, when you have an idea, you go to your lab, you do an experiment, you test your idea, and you get a result. In astronomy, we just can't visit any of these objects. We can't go and collect our data. We have to solely rely on the light we receive from our telescopes of these distant objects. But we got quite good at building telescopes, so hopefully this isn't an issue. And here I'm just bringing up the abstract from the paper that discovered this quasar, a luminous quasar at redshift 7.6. What they do in this paper is they measure the mass of the supermassive black hole in this quasar, and they find that it's roughly 1 billion times the mass of our sun. And then what I've highlighted this sentence here, where they say the existence of such a massive supermassive black hole just 670 million years after the Big Bang, because remember, if this is kind of 13 billion light years away, we're looking at it very early on in the lifetime of the universe, challenges significantly theoretical models of supermassive black hole growth. And what they're saying is you cannot grow a 1 billion solar mass black hole in only 670 million years. Even if we thought this black hole kind of popped into existence pretty soon after the black hole and just grew at what we think is the maximum rate a black hole can grow, it doesn't get to 1 billion times the mass of the sun in 670 million years. So this tells us our models of black hole growth are either too simplistic or they're wrong. I mean, we know our models of black hole growth are a little simplistic because it makes the kind of maths a bit easier. But this is one of the big questions in especially my field, is trying to work on different ways and different models of how you can actually fit these observations. So their potential ideas is, when I say growing a black hole at the maximum rate, maybe we've got this maximum wrong. Maybe black holes can actually grow a lot quicker or grow faster than we first thought. Another idea is your starting black hole, we call it your seed mass black hole, was much bigger than we thought. And if you have a bigger kind of starting black hole, you don't need to grow it as much to get it to this mass. And like I mentioned earlier, the James Webb Space Telescope has been looking into this by trying to observe some of these massive black holes very early on in the universe, and we're using that to try and kind of rule out and test theories. But the bottom line is, I mean, astronomers can correct me, but I don't believe we really have a definitive answer for this. So if anyone does have an answer, there might be, I don't know, a Nobel Prize in it for you. But yeah, this is quite a big issue, so something that we're working on. So how do we study quasars? I mean, I'm sure you'll know by now, we use telescopes. But in particular, quasars are the brightest objects in the universe, but across all wavelengths. So there's actually lots of ways to look at quasars. People use X-rays, you can use infrared, you can use optical. In my work, I use 2 optical spectroscopic surveys. So I previously been using the Sloan Digital Sky Survey, SDSS, which in the latest data release has data for about 750,000 quasars. But as was mentioned, what I've been kind of more recently working on is the Dark Energy Spectroscopic Instrument, or DESI. And this is an ongoing program. It should finish its survey next summer, and it will have data for about 3 million quasars. So kind of pretty incredible numbers. And as the name implies, it's trying to find dark energy. I'm just part of it to utilize these 3 million quasars. But it's also doing some funky things with dark energy, if that's what you're more interested in. Okay, so I've been talking about spectra, spectroscopy. So what actually is a spectrum? I'm sure everyone in here knows what a spectrum is. In terms of astronomy, we mean light split into different wavelengths. That's all it means. So like a rainbow for visible light. And a question we get asked a lot is, why use spectroscopy when we have images? And I actually had a lecturer when I was an undergrad said, don't choose astronomy if all you want to do is look at pretty pictures. And I'll be honest, a lot of what we do is look at pretty pictures, so I feel like they were wrong. But for example, this is the James Webb Space Telescope Deep Field. So this was staring kind of at a patch of sky for a very long time. You see most of these points here, apart from these ones with the big diffraction spikes, these are stars, kind of foreground stars. All of the rest are galaxies. And you can get lots of information from this image. You see these ones that the light seems to be stretched. And this is, again, because of gravity bending the light, the gravity from this massive central galaxy. And here I can pick out 3 objects, an AGN, a star, and a galaxy. And you can, with very little training, you know this is an AGN, slightly cheating because of the composite image, but it's got these really powerful jets. And only an active black hole can launch jets like this. This is clearly a star, it's just a point source. And here is a nice, beautiful spiral galaxy. So we can easily identify these objects. But my point is, these are all very nearby objects. So in terms of the scale of the universe, incredibly close by to us. So these are the objects I look at. This is real data that I took down. And I picked out a star, a galaxy, and an AGN. And I wonder if anyone has any idea which is which. So some of you might be thinking, well, this one's a bit green. This one's a bit fuzzier. But the point is, you shouldn't be able to tell. Even the color, stars, galaxies, AGN, they come in a variety of colors. And this is because these are distant objects, so we just don't have that beautiful morphological detail that we do with the close by objects. But if we look at the spectra of each of these objects, congratulations if you did get them correct. So this green one here, this is a quasar, and I've put, again, this is real data that I've taken from DESI. This is what the free spectra look like, and you can see that they look very different. So the quasar, we have these really broad kind of bumps in the spectrum, and these are very broad emission lines. Emission lines are these elements like carbon or magnesium that get excited by kind of the radiation of the active black hole. This is a galaxy. It's a bit noisy, but if you look right on the end, you should see 2 narrow spikes here. So these are, again, emission lines, but much narrower than a quasar. And that's because only these quasar objects have very broad lines. And then finally, this is a cool star. So you see these dips in the spectra, and these are molecular absorption features. But you don't need to be an expert. We can just train a machine learning model. We tell it, these are what quasars look like, this is what a galaxy looks like, this is what a star looks like. And this is exactly what we do in DESI. We don't look through millions of objects and classify them. We just feed them through this machine learning model, and it's trained on these spectra, and it automatically classifies what's a quasar, what's a galaxy. So once we have our spectrum, I'm going to stick with quasars because that's what I like. What do we do with it once I get this data? So first of all, we can measure what we call the continuum, this underlying kind of power law. And this is the direct light from this accretion disk. Because you remember, quasars have an unobscured view to the accretion disk. So this is kind of purely the light you get from this disk. And this can tell you things like how much material the black hole's consuming, the accretion rate, but also if there's dust in the system, which is something I'm interested in. But then more importantly, we can measure, kind of model these emission lines. And depending on how broad they are or how much flux, how much area is under this curve, from this we can actually measure the mass of the supermassive black hole. We can also tell whether winds are being launched by the black hole, which is one of the kind of my latest projects, and more importantly, how far away this quasar is. And that's because we know in a kind of a lab where these emission lines, what wavelength they should emit at. And then because these are distant objects, the light from this object gets stretched out, it gets redshifted, so these emission lines are pushed kind of to redder wavelengths. And there's a little equation we can use to work out then what the redshift or the distance to this object is. So all the quasars I've been showing you look a bit like this. They have this underlying continuum kind of ramps up towards bluer wavelengths. So the left is blue, and then over here is redder light. And because the reason it ramps up to the blue wavelengths is because this accretion disk, the light you get, is very blue. It's very bright in the optical and the ultraviolet. So most quasars look very blue because of this very blue accretion disk. But I'm interested in these objects, which are called red quasars. So you can see they look very similar to blue quasars. You can see that they still have these broad emission lines, but instead of rising up into the blue wavelengths, we actually drop off. And this loss of kind of light in the blue part of the wavelength is why these objects appear red. So most quasars have very blue colors, and this is because of this blue light from the accretion disk. But we found that there is actually quite an important subset that look a lot redder. And there's some that are even so red, we say that they're hidden. We can't even detect them in some of our surveys like DESI. And why do we think some are red? Well, we think the most popular idea is due to dust reddening. So what I mean by that, I have a nice photo of a sunset. When the sun sets, the sun is lower in the sky and the light has to travel through more of the atmosphere. This scatters the blue light, and so sunsets appear red. And we think a similar thing's happening in a red quasar. There's some dust somewhere in the quasar, which means the very blue light of the accretion disk travels through this dust, gets scattered or absorbed, and then that makes these quasars appear quite red. And again, real data just to show you, if you look in the optical, they literally just do look blue and red. So that poses the question, well, why do we even care that some of these quasars look a little bit red? And for the remainder of the talk, I hope I can sort of convince you that we do care, since my entire research has been looking at these objects. So I showed this slide earlier, why do we want to study supermassive black holes? And I'm going to argue that actually red quasars can give us a lot of information and help us to answer all of these questions. So understanding galaxy supermassive black hole growth, coevolution, well, if we're missing a lot of the galaxies, and we're missing especially these galaxies with active black holes because they're hidden by dust, we might be missing quite an important piece of the puzzle. In terms of supermassive black hole growth, we now believe that the most rapid black hole growth might occur in these dusty systems, which might help us with this growth problem. And then some of my work is hinting that these dusty quasars, they're more likely to have these kind of energetic jets or winds that interact with the surrounding galaxy and shape it. But I'm going to add another one that we'll just focus on, which is testing the unification model of AGN. So this is the model I showed earlier, this unified model of AGN, and I told you a quasar, unobscure view of the accretion disk. So people thought, which was the most kind of simple solution to this red-blue quasar thing, is that it just fits into this unified model picture. So a red quasar might have a more inclined viewing angle where you look through a bit of this dusty torus. This kind of is the dust that you pick up, which makes the light appear a lot redder. But in this scenario, red and blue quasars are just intrinsically the same object. It's just, again, a viewing angle issue. So in my research, I've been trying to test this theory, test the relationship between red and blue quasars. And to do this, I use spectroscopy from DESI and also radio data. Why do I use radio? Well, radio is not affected by dust. If it was affected by things like dust, you wouldn't be able to get radio in your house because your roof would block the radio. So I've been mentioning DESI. So within DESI, I have my own program that's been targeting red quasars. And just for fun, we're going to zoom into a little bit of the sky. This is using the DESI Legacy Survey Viewer, which you can have a look at. It's hours of fun, just looking at lots of cool galaxies. And if we zoom into the center, we find this beautiful spiral galaxy. And I don't care about these at all. I care about this orange dot here. This is one of the red quasars from my program that got observed. So I take all this DESI data from my program. I also then combine it with radio data. And for the study I'm going to show, I use the low frequency array, or LOFAR, which is this radio array, quite funky looking thing in the Netherlands. And I use this to try and explore the connection between radio and dust in quasars, or reddening. And this is kind of my key result. And there's quite a lot going on in this plot, well, this video. On the top, this is the percentage of quasars that I see in the radio, that I detect with LOFAR, versus dust or the amount of reddening. So if you go to the right, you get redder quasars. And I've also shown a little cutout of a representative image of one of these quasars at each of these reddening points, just to show you that the quasar itself is getting redder as you move to the right. And on the bottom is just sort of what the spectra looks like as you increase the reddening. And what we find is that the more dust or the more red your quasar, the more radio emission you have. There seems to be this connection between dust and radio emission in quasars. And why this is important is this cannot be explained by this unified model. Because if red and blue quasars were intrinsically the same object, then we wouldn't expect any differences in the radio emission. So this means something else is going on in red quasars. And my theory, and yes, I did put this schematic together myself, is that the radio emission in these dusty quasars is enhanced because there's winds or jets that are being launched from this active black hole that then hits the dust in this quasar, it shocks it, and these shocks produce radio emission. And if you have more dust, you have more of these dust clouds, you can imagine that you're more likely to intercept one of these dust clouds with your winds or your jets. And that's why I think you see this connection. And what I mean by winds and jets is something like this. I quite like this animation. When we refer to a jet, we just mean this very collimated, highly relativistic stream of particles. A wind is something a bit slower, that's a bit more diffuse. And kind of what I'm working on at the moment is, can I distinguish between these two mechanisms in terms of what's causing this connection? And turns out that's quite hard, so for now I say wind/jet. And why I think this is very exciting is if you're shocking your gas, if you're slamming a wind or a jet into the dust, this will heat the dust up, and either you destroy the dust or you blow the dust away. And if you keep removing dust from your system, you're going to get bluer and bluer and eventually just turn into a typical blue quasar. So what I conclude is that red quasars might actually be an important phase in the evolution of quasars and maybe in the evolution of galaxies. So this is kind of a comic strip where you start with two merging galaxies. That then creates a lot of dust and chaos, and you funnel a lot of material to the center into your black hole. It becomes active, but it's initially dusty, and then through these winds and jets, we reveal a typical blue quasar. And then when this quasar runs out of material to feed the black hole in the center, it, what we call turns off. It's no longer a quasar, and it's just a typical dormant galaxy. So why do we care that some quasars look red? Well, I argue they may hold the key to galaxy evolution. Okay, so in the last minute, looking towards the future, I keep mentioning JWST. Every day it produces an amazing photo. This is one of my favorite, which is like 4 galaxies that are merging at the same time. We also last month had the first light of a new spectroscopic instrument, the 4-meter multi-object spectroscopic telescope, or FORMOST. So this is going to give us even more spectroscopy of quasars and AGN. Something I'm involved with is this infrared spectrograph called MOONS. This is my photo when it was built in Edinburgh, and it'll eventually get shipped to Chile, put on the VLT, and hopefully will be on sky at the end of next year. So we'll get infrared spectra, which opens up kind of new areas of science that we can do with spectroscopy, since DESI was optical. The Square Kilometre Array, or SKA, is the next generation radio telescopes, which will be in South Africa and Australia. Again, this will revolutionize radio astronomy, and I believe 2030s, early 2030s. And then I couldn't give a talk without mentioning everyone's favorite, the extremely large telescope, the ELT, which is currently being built. So this is what the ELT will look like. Again, it's in Chile. These are some cars to give you a sense of scale. It's going to be the largest telescope in the world when it's finished. Again, 2030s, give or take. And what was quite exciting is this video is from 2 weeks ago, and we finally tested the doors, the kind of doors to the dome, and it seems to work. So you can see that we're at a quite exciting stage. It seems to be sort of on track, but I guess you should never really say that in astronomy. So yeah, lots of things coming on sky. So I'd say the future of astronomy is looking very bright and very exciting. So thank you very much, and I'm happy to answer any questions.
Vicky, great stuff. If you have questions in the room, please wave your arm and can I pull the lights up? Wait until a mic comes your way. And if you're online, then please put it on Slido, and it'll go through to me on this magic machine down here. So first in the room. Yes, sir. Well, wait for the mic.
Thank you. Can you hear me all right? Good. Doctor, you talked about the torus, the dust torus that's within these quasars. Can you tell me, is that dust held by the gravity that still exists within the black hole?
Yes. Yeah, so it's
Sort of in suspension?
Yes. It's just further out than the accretion disk, but it's still kind of in place because of the gravity.
Yes, so it's mass versus the gravitational pull leaves it there. It's not disappearing into the black hole immediately.
No, so it's only kind of the inner part of the accretion disk that's kind of spiraling in. The dusty torus is relatively quite far out. I mean, we think that the radiation of the accretion disk could be heating up. This is kind of what my latest project's looking at, heating up the inner edge of the torus and kind of blowing some of the dust away. But yeah, it won't be, it's too far away to be kind of falling into the black hole. It won't kind of collapse.
Because I was wondering whether the mass of the torus is acting a bit like a venturi that forces energy to go out upwards rather than through the dust itself.
Yeah, I'm not quite sure what you mean by that.
Well, having a torus ring around this energy, does the mass of the torus itself force the energy to go up and down rather than out sideways, I guess? Yeah, well,
there's definitely some. So I don't know too much about kind of like accretion disk theory, but there's models that every time I show an accretion disk and a dusty torus, it's quite a simplified model, and there's different models that, depending on like the accretion rate and like what the black hole's doing, the accretion disk itself can puff up rather than just being this kind of thin disk that we thought for quite a long time. We now think that there's actually a range of these puffiness, which then kind of might lead to the dusty torus. But I'm not too sure how that relates to my work, but I do work with someone that does a lot of this modelling. And it depends on the accretion rate and other factors like the X-ray properties. But it's something I haven't really looked into. I just used a fairly simple model for now.
It's just that obviously the dusty torus is the common feature in various guises with all these quasars, which is obviously what your specialism is studying. Thank you.
While the microphone's here, yes. Thank you very much. That was a lovely talk. Brings back a lot of history for me. There's a lot of energy being generated in quasars and black holes. We're perhaps fortunate that the Milky Way doesn't have an active black hole in the moment. One of the previous chairwomen of the committee that selected Caroline Herschel lecturers, Diana Worrell, and I worked on an object called Parkes 2152-69, which has a very, very intense jet, which seems to be interacting with perhaps a dwarf galaxy next door. I wonder if you'd given much thought to the effect on possible planetary life of having a very active supermassive black hole in the center of a galaxy.
Yeah, I think there have been people thinking about this. So the question is, if our Milky Way suddenly became a quasar, what would happen to Earth? And I think it's a bit of a complicated question. I think if we were closer in, then maybe the intense radiation field would not be a good thing. Again, if it did have this jet, and we happened to be, definitely if we were in the line of sight of this jet, really bad. But if neither of those occur, and we're at the outer edge, and we're not close enough to this radiation field, and we're not in the line of sight of this jet, I think people are speculating that maybe it would be fine. But we don't know for sure. But we don't think it's the end of the world if that happened. But there are definitely, it would be harder to have life, especially if your proximity to the quasar.
High mutation rate.
Potentially, yes, with the gamma ray and X-rays, yeah.
Question here.
Do black holes stay black holes forever, or can they ever evolve into something else?
Short answer is no. I mean, I don't know if I can get my slides back. So yeah, short answer is no. Once you get it, they're pretty stable, as in they're just gonna be black holes forever. And most of the time, because they attract material, if you'll constantly feed the black hole, it's just going to get bigger and bigger and bigger over time. And it will just stay that way forever. If you're in a circumstance that there isn't anything feeding it, it's isolated and it can't get bigger from consuming material, then there is this weird, my crazy backup. There is this weird concept that people have probably heard of Hawking radiation, which is very strange. In a vacuum, you get particle-antiparticle pairs that pop into existence and then out of existence all the time. And the theory that Stephen Hawking said is, well, if you have one of these pairs close to the black hole might, the antiparticle might fall into the black hole, and then this particle will escape. And this is the Hawking radiation. So it's this theory, I think we have sort of proven this now, that black holes do actually, to some level, radiate. And because of this radiation, they actually lose mass over time. I mean, it takes a very long time for this to happen. But in theory, if you have an isolated black hole, eventually it will just get smaller. We could say it evaporates, smaller and smaller and smaller, and then pops out of existence. And again, there's some information theory that's probably beyond me that says information cannot be destroyed. So if your black hole disappeared, it would then release the information of everything it consumed over its lifetime. But this gets a bit too theoretical for me, but that's kind of the ways that a black hole can change. But short answer is they just stay black holes. Yeah.
Question online. What kind of process do you need to go through to use the group of telescopes to observe these objects? In other words, all these massive collections between telescopes.
Yes, that's a good question. So there's kind of three ways to get telescope data. There's public data. So DESI, for example, you guys could all go online and download the latest data release of DESI and do your own science with that. You can be in a collaboration. You get kind of first access, first dibs to the data. So like I'm in the Moon's collaboration, so when they start taking data, it won't immediately be public. Or the other way, which I've also done a bit of this as well, is that you say, I want to look at these 10 galaxies with this telescope, and you write a proposal. You say, this is why I want to look at these 10 galaxies. This is why I want to use your telescope, and this is the amazing science I'm going to do with it. And then it goes to a panel. They assess all of these applications because there's not a limited time on these telescopes, and then they choose the most exciting science and give you time, and that's your own private data. So they're the kind of ways. And then these days it's all automatic, so I've got time on the VLT in Chile, and I didn't need to, I mean, it would have been nice to go to Chile, but I didn't need to. The telescope operators did it, and then just emailed me the data once it was taken.
Okay, another question.
Sorry, this is quite basic probably, but going back to the representation from Interstellar, we got this like perfectly black sphere for the black hole, right? And what's inside is something of a mystery. From the fact that we have a secretion disk, we think of it being a disk, and it could have bulges, and then you have these jets. Do these external features tell us anything about what's inside the black hole? And why is it a disk? Why is it not a secretion sphere in that sense, given that the black hole itself is a sphere?
No, that is a really good question. So in terms of can it tell you about what's inside the black hole? No, and unfortunately it's got one of the mysteries. Well, I believe it's one of the mysteries of the universe is that we'll never know what's inside a black hole, because even if we sent in a drone, the drone would never be able to escape. If it tried to send out radio signals, the radio signals would never be able to escape. In terms of why it's a disk, is because, I mean, everything in the universe more or less is spinning, just kind of how it forms. You know, stars spin, and when they collapse down, when they get smaller, it's a bit like someone ice skating, and when they do like a pirouette and then they put their arms in and they go really quick. So black holes kind of spin quicker than their stars, and then it's the conservation of angular momentum causes this disk to be a disk. And black hole is spinning, yes, yes.
Okay, another question online. You need at least one generation of stars to make all the elements in the dust. So would we expect the younger, higher redshift quasars have a different torus?
Oh, that's a good question. I think people are looking into this. So it's something called, it's a property of galaxies that we say metallicity. And it's a weird thing. In astronomy, anything that's not hydrogen is a metal. So there is this idea of that things earlier on in the universe are more, we call them pristine. So people do look at this metallicity as a property that can distinguish, the dust and the stars within this galaxy. And it's something I have been meaning to look at in terms of the differences between red and blue quasars, like look at the metallicity. And honestly, I haven't got round to do it, but that is a good idea, because you might expect a difference in, well, at least the stellar populations for these higher redshift ones.
I think the question has just triggered some more work for you.
Yes.
Any more questions in the room? Over there, sir. Yeah.
Is there a theory that supermassive black holes started as minute rents in the inflationary ball of energy at the beginning of the universe?
Wow. So I think there is. I've got to say, I'm not an expert on this, but I think there are some theories in terms of, so inflation's when you go for the Big Bang and then you inflate the universe very, very quickly. and then you get these kind of ripples due to quantum effects. And there are ideas of how you would birth black holes in this kind of inflationary stage. And I think that's one of the ways people are trying to reconcile this black hole growth problem, is if that occurred, then maybe these things would grow much, much more rapidly really early on in the universe. And that's like the step that we're missing. But I won't claim to be an expert on this, so I will say maybe, but I'm not too sure. Yeah, sorry.
Another one online. For the X-ray binaries you mentioned earlier in your talk, what is the typical distance at which this interaction was taking place?
Oh, so so I think this depends on the mass of the black hole and the mass of the star in terms of how close you need to be for this this kind of overflow process of the star going onto the black hole. Because we found lots of binary systems where you don't have this kind of stripping of the star, that they're too far apart, they're just orbiting each other. So they don't have to be in this this is like the most extreme version of these black hole binaries. But in terms of, the exact distance, I don't know off the top of my head, and it does depend. It depends on mass as well of the two systems.
Okay, thank you. Another question in the room? Any more? Yes, sir, over there.
I had two kind of basic questions. I was wondering, earlier in the talk you mentioned binary black holes, and you said you wouldn't have time to talk about it. Can you explain what they are?
Yep. Could I go back to my slides, please? So kind of another famous way we can find black holes is if you have two black holes that are orbiting, eventually they'll get close enough, and because they both have a lot of gravity, that they actually merge together. And this is a very violent process, and it's so violent, and they have so much gravity that what happens, if you think back to this blanket definition, is you actually create ripples in space-time, like kind of throwing a pebble into a pond. And these ripples kind of travel out and will intersect the Earth. And what these ripples in these gravitational waves, these ripples in space-time, they actually kind of change the kind of distance of objects. They kind of shrink and expand space itself, which is kind of weird, but we actually can measure that. We do using interferometry instruments called LIGO and Virgo. We kind of shoot lasers off and measure the distance that the laser takes to kind of reflect and exaggerated effect. And we can literally measure them, the lasers kind of changing distance, if that makes sense. When a gravitational wave comes through, they sort of do this, and we can detect that as a signal. And it's incredibly subtle, but we've done it. And we actually are working on LISA, which is a space-based gravitational wave detector that will be even more sensitive and be able to detect this with smaller black holes. Because at the moment, we can only really detect the most massive black holes because this creates the most, the strongest gravitational waves. And here's a collection of, in the blue, is all the black holes we discovered via gravitational waves. And in the red is kind of like this X-ray binary systems I've been talking about. So you can see it's a very, very effective way of measuring black holes. So it is by detecting these gravitational waves, and then from measuring these waves, we can then work out what the mass of these two black holes, which are shown kind of there, and then the arrow shows the final mass of the final system. Because if you add two black holes together, you just make a bigger black hole. So I hope that answered your question.
Okay. Yeah, second question.
Could we eventually make a black hole like scientists?
I remember this being a concern when they switched on CERN, that we were going to create a black hole. And I think the papers ran with this, that scientists were creating a black hole that was going to destroy the Earth. That didn't happen. I would say no. I guess nothing's impossible. Hopefully scientists would draw the line at that point, because you need, you know, a star that's 20 times the mass of our sun to collapse, and so that it takes an incredible amount of energy, and you have to compress an incredible amount of mass down. So, I mean, it's a good question, but I said I would guess that that's pretty far into the future in terms of what we're capable of doing, and hopefully we wouldn't do that.
We have time for one more question. This is online. If we had a spaceship faster than the speed of light, could we exit a black hole?
Short answer, yes, but nothing goes. That's one of the pretty fundamental laws of physics. Nothing goes faster than the speed of light, so we wouldn't be able to do that. Yeah.
Well, Vicky, thank you. It's been a great lecture. I found it quite fascinating, this story of these supermassive black holes and why the dust matters. I must say, I thoroughly enjoyed the visuals. I think they're quite stunning. And the one that struck me was the one we saw very recently, was the wobbly Earth. So all those times when you feel a bit tricky after a hard night out, you can blame gravitational waves rather than what you've been drinking. So please, thanks Vicky again for her wonderful talk.